Hello, in this presentation, we are pleased to present our final project for the Special Topics in Control and Automation Engineering course. We will provide an overview of the project's objectives, methods, and results. Our project focuses on the real-life implementation of a quadrotor system, with the primary objective of minimizing noise in data received from sensors. In real-world applications, sensor measurements are often affected by various types of noise, which can compromise the system's accuracy and performance. To address this challenge, we aim to develop and implement effective filtering techniques to process the noisy data, ensuring that the system operates reliably and delivers precise results. By minimizing the impact of noise, our approach enhances the overall stability and efficiency of quadrotor system in practical applications. A quadrotor is a type of unmanned aerial vehicle that is powered by four rotors. It is known for its stability, maneuverability, and ability to perform complex flight maneuvers. Due to its compact design and ability to hover, the quadrotor has become a valuable tool in various applications, such as surveillance, environmental monitoring, search and rescue operations, and scientific research. The system's control algorithms allow for precise navigation and data collection, making it ideal for tasks that require high accuracy in dynamic and challenging environments. Noise in sensors refers to any unwanted or random variations in the data produced by the sensors. These variations can distort the true signal, leading to inaccuracies. Essentially, noise is any interference that reduces the sensor's ability to provide precise and reliable measurements. Noise can significantly impact the performance of the systems that depend on sensor data, such as quadrotors, by making it more challenging to process the data accurately. This, in turn, can result in potential errors in the system's operation. Let me explain a few common types of noise that can affect sensor data. First, thermal noise occurs due to temperature fluctuations inside the sensor. This happens because the random motion of electrons increases as the temperature changes. For instance, imagine a temperature sensor placed outside on a windy day. The readings might fluctuate not because the temperature is actually changing, but because the internal heat of the sensor itself is causing these variations in the data. Next, we have electrical interference. This type of noise happens when the external electromagnetic fields distort the sensor's signals. For example, consider a drone flying near power lines. Its sensors might suddenly start producing erratic readings, which can throw off its navigation, making it harder to maintain stable flight. Lastly, there is sensor drift, which refers to the gradual change in the sensor's performance over time. This happens when the sensor's output shifts slowly, even if the actual measured quantity hasn't changed. For example, a pressure sensor in an industrial setup might show slightly inaccurate readings after a few months of use. This drift can lead to incorrect data unless the sensor is recalibrated regularly. These are just a few examples of how noise can affect the accuracy and reliability of sensor data, which is why filtering these disturbances is so important in many systems.
Noise and filters are closely related in sensor systems. Noise refers to any unwanted or random variation in the data that can distort the true signal. A filter is a device or algorithm used to remove unwanted noise or interference from a signal, allowing only the relevant or desired information to pass through. It works by identifying and reducing disturbance, improving the accuracy and clarity of the data. In this way, filters help ensure that the data collected by the sensor is as improving the overall performance of the system. By minimizing the impact of noise, filters enhance the reliability and accuracy of signal measurements, which is especially critical in applications requiring high precision. Extended Kalman filter is a widely used algorithm for state estimation in nonlinear systems. The extended Kalman filter adapts the strength of the Kalman filter to nonlinear scenarios by linearizing the system model with Jacobian matrices. The extended Kalman filter works in two main steps. In the prediction step, the next state is predicted using the nonlinear system model, approximated by the Jacobian matrices. Then, in the update step, the prediction is corrected using incoming measurements, minimizing the difference between in the prediction and the actual measurement. The diagram on the slide illustrates the extended Kalman filter process. We start by initializing the system with an initial state estimate and covariance matrix. As new measurements are received, we predict the system's next state using its nonlinear model. The Kalman gain, calculated in step 4, helps combine the prediction and measurements in an optimal way, updating both the state and its uncertainty. This process repeats for every measurement, ensuring the system's state estimate becomes increasingly accurate over time. Extended Kalman filter is essentially in applications such as navigation, robotics, and sensor fusion where nonlinear dynamics are involved. Now, let me introduce the particle filter, a robust algorithm for state estimation in nonlinear and non-Gaussian systems. Unlike the extended Kalman filter, which relies on linearization and Gaussian assumptions, the particle filter uses a set of weighted samples or particles to approximate the posterior distribution of the system's state. The process begins with initial sampling, where particles are distributed that represent the prior state of the system. In the sequential importance sampling step, particles are propagated forward based on the system's dynamics, and their weights are updated using the likelihood of new measurements. Finally, in the resampling step, particles with higher weights are duplicated while those with negligible weights are removed. This step avoids the issue of particle degeneracy, ensuring that the particle set remains a good approximation of the posterior distribution. The diagram on the slide visually explains these steps. You can see how the particles evolve through sampling, weighting, and resampling to ultimately match the true posterior distribution. This technique is particularly useful in applications such as robotics, target traction, and sensor fusion, where nonlinear and non-Gaussian characteristics are common.
In this slide, we demonstrate the performance of the quadrature system in a simulation where no noise is present in the sensor data. As shown in the graphs, the controller operates efficiently, maintaining precise control and stability throughout the flight. With clean data from the sensors, the system can follow the desired trajectory smoothly and with minimal error. This scenario highlights the ideal condition in which the quadrature functions optimally. In this slide, we compare the performance of the extended Kalman filter and the particle filter based on our system model, which simulates a real quadrature. The filter were applied to this model to estimate the state of the system under noisy sensor data conditions. As shown in the graphs, both filters effectively estimate the system states and manage the noise. The extended Kalman filter, which is computationally efficient, worked well for systems with relatively mild nonlinearity. However, when dealing with more complex nonlinearities in our quadrature model, the particle filter demonstrates superior performance, providing more accurate state estimates. Our results indicate that both extended Kalman filter and particle filter are well suited for the quadrature system model we have developed. Despite the higher computational cost of the particle filter, it offers more robustness when facing highly nonlinear dynamics and noise. On the other hand, the extended Kalman filter remains efficient for less complex situations where the system dynamics can be linearized. The main takeaway is that that while both filters are compatible with our system, the choice between them depends on the system complexity and the need for computational efficiency. In our case, both filters perform well, but the particle filter preferred when handling more complex nonlinearities in real-world applications. In conclusion, both the extended Kalman filter and the particle filter proved to be effective for estimating the state of our quadrature system under noisy conditions. While the extended Kalman filter is computationally efficient and works well with systems that can be linearized, the particle filter shown its strength in handling highly nonlinear dynamics and noise. Our results indicate that both filters are compatible with our system model, and the choice between them depends on the complexity of the system and balance between computational cost and accuracy. Overall, this comparison highlights the importance of selecting the appropriate filtering technique based on the specific challenges of the applications. Thank you all for your attention. I hope this presentation gave you a clear understanding of how we compare the extended Kalman filter and the particle filter for our quadrature system.